So the last lecture, we basically learned about Dole-Strong protocol. So this is like our first encounter with distributed consensus. And there was an excellent question that was raised during the lecture, right? So remember in the Dole-Strong protocol, we needed signatures. The nodes have to sign the messages. And in order for the signature, to work, what we actually need is what's called a public key infrastructure, right? Public key infrastructure. This is also called the PKI. And the PKI is essentially a setup. Like, we are assuming at the beginning of the protocol, all the players' public keys are common knowledge. Everyone knows everyone else's public key. So now one question that was raised is like, is the digital signatures and the PKI necessary, right? So is the PKI, the signatures necessary? Maybe I should say are. So we are going to try to answer this question together in today's lecture. Okay, so the last time we quickly discussed this question, and the signature is like serving some purpose, because with the signature, like one thing we can do is, let's say Anoop sends a message to Ke, and Ke wants to convince string C that Anoop indeed, let's say, said yes. So in this case, Ke can just demonstrate Anoop's signature on the message yes, and then string C can be convinced that Anoop indeed said this. And let's say if Anoop is malicious and he signed both yes and no, essentially Ke can also demonstrate evidence that Anoop, voted ambiguously, right? So the point is that, like with signatures, what we get is some kind of transferability. Like transferability is the ability, like for me to convince you that, let's say, Anoop said something. Another way to think about it is like it provides some kind of non-repudiation. Like if Anoop voted ambiguously, like the evidence can be passed on too, so there's no way he can like deny the fact that he voted ambiguously. And without digital signature, like we don't have the transferability and the non-repudiation. And what happens to consensus? So why is this question motivated? Why do we care about, like, let's say, consensus protocols without PKI and signature? Signature is what we use all the time, like on the internet. I mean, in some cases, there are advantages. So number one, like as we know, PKI is actually difficult to manage in practice, right? Like the biggest PKI infrastructure deployed in practice is the certificate system for all these websites. And you might have heard about a lot of pain points, like to manage this certificate system. Like there's a lot of headaches, like regarding revocation, evolving, updating the certificates, and sometimes there's like man-in-the-middle attacks for managing the PKI. And another reason you might care is because of performance. Like sometimes, signing, it can take like a millisecond to sign the signature, but let's say if the consensus protocol is deployed in environment like Google or Facebook, right? I mean, they have really high throughput, and we care about microsecond latency. So in these cases, like you don't want to spend 1 millisecond just to sign the signature, right? So this question is meaningful to ask because of two reasons. Like one is PKI can be a headache to maintain in practice. Like, basically, you can think about the web's certificates. And then the second reason is because of performance. And here, like the example is like, you know, in Google, Facebook settings, they want, let's say, microsecond confirmation latency. Okay. So the theorem we are going to prove today is that without PKI signatures or any other setup assumption, consensus is actually impossible. So we actually learned the abstraction Byzantine broadcast. So I'll write Byzantine broadcast is in fact impossible if at least 1/3 of the players are corrupt. If at least 1/3 of the players are corrupt. So this is the theorem. Okay, so it's interesting to contrast this with the Dolev-Strong protocol we learned, right? So remember, in the Dolev-Strong protocol, you can tolerate arbitrarily many corruptions. But now we are saying if you remove the ability to sign, you know, something like that should not be possible. Like the best you can do is to tolerate strictly fewer than 1/3 corruptions. So this is also actually tight, because in the next lecture, we can actually learn an upper bound. We are going to essentially learn a consensus protocol that doesn't make use of PKI or signatures, and it can secure against strictly fewer than 1/3 corruptions. Okay. So how do we prove this? I will first actually give a slightly incorrect proof, like it gives the intuition, it's not really a proof. And then I'll tell you how to actually turn it into a correct proof. So the incorrect proof is just like the intuition we have talked about, because we have lost this transferability, you know, without signature. So imagine in Cranberry Mellon University, let's say the scenario we have is in Cranberry Mellon University, they want to elect the next university president, right? As we all know, the current university president is Farr. And basically the next president, there are two candidates, more and less. So they want to run the consensus protocol to do the election. And let's say Farr is the designated sender, like he has a candidate in mind. And let's say, you know, he wants to propose more to be the next president. I mean, of course, president is like, you know, has too much work. No one wants to be president. So Moore wants to get out of it. So let's say they run a consensus protocol, and Farr will send suggestion more to both more and less. Okay, because more wants to get out of it, so she will actually tell less. So these are round 1 messages. Imagine, right? And then in round 2, more will relate to less. Let's say far said, far actually said more, but she will say far said less. And then, I mean, less, let's say, is honest, and he will just say, you know, far said more. And in this example, the issue is that there's no signature, right? So there's no way when Mar says, okay, he said less, there's no way for less to verify if actually Mar relayed the message correctly. So there are 2 possible scenarios. One is that Mar is malicious, right? I mean, far is honest. Like the scenario 1 is like far and less are honest, and far actually made consistent suggestions to both more and less. But more is malicious, so she basically changed the message. That's scenario 1. And in scenario 2, you know, more could be the honest person, and far is dishonest. Like let's say far actually indeed made inconsistent suggestions to these 2 players. Like he could have suggested less to more and suggested more to less. And in this case, you know, more would be relaying this message, and she is actually acting honestly. So in some sense, less has no way to distinguish between these 2 scenarios. So what are the 2 scenarios? Like scenario 1 is when far and less are honest, and more essentially modified far's message during the relay. But then in scenario 2, more and less are both honest, and then far proposed inconsistent suggestions to more and less. So essentially, less has no way of distinguishing between these 2 scenarios, cannot distinguish between the 2 scenarios. And you know, less cannot distinguish because we don't have signature, right? There's no way to verify if, you know, more has altered the message. So this is like supposed to give some intuition. I mean, obviously it's not a proof. Like to start with, like why is this not a proof, right? I mean, it should be obvious that it's not a proof, because like to start with, like who says the protocol, you know, must do this, right? Who says the protocol must begin with, like, let's say in round 1, and far takes some action, and in round 2, you know, they relay the message. Like our theorem statement is actually ruling out any protocol, right? Any protocol that, you know, tries to achieve Byzantine broadcast against 1/3 or more players, like it's essentially impossible. Okay, so how do we turn this very rough intuition into a correct proof? So the key is that this intuition, like, is what, you know, you can remember very well, right? It's a triangle. But the correct proof, the key takeaway is the correct proof is a hexagon, it's not a triangle. So you'll see what I mean. So let me first write it down. The key takeaway is the correct proof is a hexagon, not a triangle. Okay. So joking aside, let's now prove the theorem together. Okay, so first, let me call this theorem 1. And we're going to prove theorem 1 together. Proof of theorem 1. So I want to say this theorem was actually first proposed by Peace, Shostak, and Lamport in 1980. PSL 80 was the first paper that proved this theorem, but the version we are going to present is actually due to a later simplification by Fisher, Lynch, and Merritt, FLM. And this is the version we will present. Okay. So as I said, it's a hexagon. So let me first draw the hexagon for you, right? We have 3 players, far, more, and less, right? So M, F, and L. You may have noticed that the initials are also consistent with the author's names, FLM. Okay, so that's the hexagon, and the F is the sender. So there's F and F prime. F receives the input 0, and F prime receives the input 1. Okay, so the biggest challenge to overcome, actually, to get comfortable with this proof, you need to get comfortable with the idea that this is a 3-player protocol, but now I'm going to execute it with 6 nodes in this fashion. So I want to argue that this execution is actually well defined. Like, even though it's a 3-player protocol, right? So what does it actually mean to execute it like with 6 players? And why is it even well defined? The point is, if you look at every player, M thinks it's talking to F and L, right? Like in the 3-player protocol, M thinks it has 2 players that it's talking to. I mean, here it's the same. M thinks it's talking to F and L. So it's just going to run whatever, the protocol tells it to do. Whenever it receives a message here, it's a message from F, and whenever it receives a message from here, it's a message from L. And whenever it needs to send a message to F, it sends this way. Otherwise, it needs to send a message to L, it sends this way, right? So from the single node's perspective, actually the execution is well defined.
Elaine, I'm sorry, I have a question. I probably missed it, but why is M not talking to M prime and F prime and so on?
So the important thing is for the execution to be well defined, and every player needs to have 2 neighbors. Like this is a 3-party protocol, right? If you think about it, okay. What does a 3-party protocol do? Like, I expect that I have 2 neighbors. So there's 2 outgoing pairwise channels that I'm on, and I'm observing incoming messages on these 2 narrow channels. And then I send messages over these 2 channels too. So like, essentially, every player cannot have like 3 links, and otherwise the execution is eerily defined. But when you connect it this way, like, it's actually a well-defined execution.
Okay, I see.
Mm-hmm. That's also kind of like the coolest idea in the proof. Like, I wonder how they thought of it in the first place. But I think once you are comfortable with this 6-player execution, the rest of the proof is actually pretty simple. So this is again, the hexagon is the key idea behind the proof. Like it's the most elegant idea, in my opinion. Okay, so now, yeah.
Signatures, how can M verify that it really did receive a message from F on that link, and it really did receive a message from L on the other link without signatures?
So let me try to interpret this question. Like M doesn't know what's going on here. M cannot see what's going on here, right? Like it's just following the protocol. When it receives a message on this link, the protocol learns that some message has been received from F. When it receives a message on this link, this program learns some message has been sent from L, and then it runs the program, decides what message to send to F and L. So it only basically, I mean, if you think about what is a program in the protocol, right? It reads messages from 2 incoming channels because this is a 3-player protocol. And then it sends messages, it computes something locally, and then it sends messages to 2 outgoing channels.
Right. But without signatures, there is some sort of association between the link and F so that it knows that it's F's message on this link because F has not signed the message to M, right? Yeah,
there's no signature. So if you're asking why the proof doesn't work with signature, that's exactly why, because like once you see the proof, you'll know, like we will reason about this execution and we are going to reach a contradiction. And like if the protocol adopts signatures, then in the middle of the proof, like we are going to interpret this execution. For instance, one way to interpret it is that, let's say F is the corrupt player. So actually, why don't I just begin with the proof? And when we come to the point, I can point out why the proof would actually fail to work if the protocol involves signatures. I mean, obviously the proof shouldn't work if there's signature because we've seen the upper bound, we've seen toe left strong, right? Okay, so I think, I mean, now is the time. Yeah, yes, go ahead.
So one question I had is, are we assuming that senders can prove their identity? Like, what if more claims to be far and then says that okay, I'm proposing less?
So that's an excellent question. So actually, let me clarify the model. We are going to assume the authenticated channel model.
I see. Yeah, that's what I was asking, because without signatures, can you still assume the authenticated channel model?
Oh, yes. So we are actually assuming authenticated channels. So in the authenticated channels model, essentially, you know who you are talking to. Like I know the message on this link is coming from far, and the message on this link is coming from L. For a lower bound, this gives you a stronger lower bound, because if it's impossible in authenticated channels model, it should not be possible in unauthenticated channels either, right, in some sense. Because authenticated channel is like, in some sense, an assumption, an additional assumption that you have.
Got it.
Okay.
So just to clarify, it basically means that if you send a message directly to me, I know you said it. But if you said, Ke said something, then I cannot prove it.
Yeah, if you, that's exactly right. If I send it directly to you, you know that I said it, but you just cannot convince anyone else that I said it.
Okay, got it.
Okay, so these are great questions. Any other questions before I continue to do the proof? Okay, so now let's do the proof. Like I said, the proof is actually, like the entire proof is just different ways to interpret this experiment. So once you're comfortable with this experiment, right, this experiment is well defined, and now we will interpret it in 3 different ways, and we will apply the consistency and validity properties to each interpretation, and finally we will reach a contradiction. And the contradiction will basically allow us to rule out the existence of a three-player protocol that defends against one corruption. So essentially, the rest of the proof is going to be like this. Assume there exists a three-player protocol that defends against one corruption. We will be able to reach a contradiction using this experiment, right? So let me first write down the high-level idea of the proof. Suppose, for the sake of reaching a contradiction, that there exists a three-player protocol that defends against one corruption. We will use the hexagon experiment to reach a contradiction. And then the contradiction will essentially allow us to rule out the existence of a three-player protocol that defends against one corrupted player. Okay, so it's all about interpreting this hexagon experiment, and there are different ways to interpret it. Okay, so interpretation one. Now let's imagine it's actually a three-player protocol. There's only three players, F, L, and M, and F is the corrupt player. So imagine F is simulating all of this parts in its head. So essentially, you know, F is a program, right? I mean, F is like a program can, you know, when we learned about Turing machines simulating other Turing machines, like a program can simulate other programs, right? So imagine this program is simulating all of this in its head. Okay, so in this interpretation, what can we conclude? So F is the corrupt player, right? Because it's simulating all this stuff, it is not running the honest protocol. It's like running something else. It's running the simulation of all of these players. But if like the protocol we are running defends against a single corrupted player, it means that the honest players should still have consistency. So in this case, L and M are honest, and they should be consistent among themselves. Okay. So I'll have to like scroll up and down a little bit. Let me write down interpretation one. This is a three-player execution. Of the protocol pi, right? So actually, let me name this three-player protocol pi. And then this hexagon experiment is executing pi. Okay, so first imagine this is actually a three-player execution of pi. And I think I said F is the corrupt player. And F is simulating the part, essentially the part F, L prime, M prime, F prime. Okay. So in this case, we will apply the consistency property of pi, right? Pi is secure if a single player is corrupt. So by the consistency of pi, L and M should agree on the decision. Okay, so that's interpretation 1. And now we will have 2 other interpretations of this execution. Interpretation 2. Okay, so let's go back to the hexagon again. So what is interpretation 2? Okay, interpretation 2, like we are going to imagine this is actually a 3-player execution involving FL and M, but imagine L is actually the corrupt party. Like L is simulating all of this bottom parts in its head. So all of this is executed inside a single player's program. And again, you know, we know that pi is supposed to defend against a single corrupted player. And in this case, you know, because F and M are honest, right? So this is the corrupt party, these 2 are honest. And we can conclude by validity that M needs to output put the sender's decision, right? The sender is F, it has the input bit 0. So M should output 0 by validity of pi. So just very quickly again, imagine it's actually 3 players, F, L, and M. And this is a single node, L, which is corrupted. F and M are honest. By the validity property of the protocol, M should output the sender's input bit, which is 0. Okay, so let me write it down. Interpretation 2 is imagining that this is actually a 3-player execution of pi involving F, L, and M. I guess here it's the same. It's involving F, L, and M. But in interpretation 2, L is the corrupt party. And it is simulating all the bottom part of the execution, which is L prime, L, F prime. So all of this is being simulated by L. Now, in this case, by validity of pi against a single corrupted player, M should output 0. Which is F's input bit. Okay, so we are almost there. So far we use consistency to conclude that L and M must be consistent, and we use validity to conclude that M must output 0. And if I can have a third interpretation that says that L should output 1, then that's sufficient to reach a contradiction. So what is the third interpretation? Can you think about it? So what I want is to have a third interpretation and conclude that L must output 1, right? So far we decided L and M must be consistent in interpretation 1. And then we decided that M must output 0, and that's in interpretation 2. So what about now, let's have an interpretation 3 and conclude that L must output 1. And then we reach a contradiction.
Before that, like I had a small question, like, first of all, what does it mean that F is simulating that F, L prime, M prime, and F prime? And secondly, like the different interpretations, they assume that a different node is corrupt. Is that even allowed? We're assuming only one corrupted player can be there.
in each interpretation, we are assuming a single player corrupt. Each interpretation is like a 3-player execution in which 1 player is corrupt. So, because this is just another way to view the experiment, right? So one way to view, let's go over interpretation 1 again. In interpretation 1, we are viewing it as a 3-player execution, and there are 3 players, essentially F, L, and M. But F is the corrupt player, right? Corrupt player doesn't have to execute the honest program. It can execute any program. And specifically in this case, the program it executes is all of this. Like, you know, a program can simulate other program. Right? I can write an interpreter, you know, like in compiler class, we learned you can write an interpreter, you take another program, you just run it with the interpreter. So imagine like F is, you know, taking all these programs and just running all of this.
It doesn't matter like what's going on between L prime and M prime, or it also doesn't matter what's going on between F and L prime and F prime and M prime. So the only thing matters if F is running all these 4 nodes is what's going on between F, M and F prime L, right?
For the whole proof, it matters because the way we reach a contradiction is that it's actually the same.
But I mean,
so
like in this interpretation.
Yeah, what we want is actually to reason about the same experiment. Like the experiment has to be the same, but it's just 3 different ways to look at it, right?
Okay.
And then because it's actually the same experiment, like we just look at it in 3 different ways, reach different conclusions, and in particular reaching contradicting conclusions, we can rule out the existence of such a protocol. So it is important that all the 3 interpretations are actually talking about the same experiment. It's just different way to view it.
Okay.
But why can you assume in different interpretations the different nodes are correct, are corrupt, and still be able to say that all of the findings from each of the interpretations must hold together? Like you're saying that consistency from interpretation 1, that L and M agree on a output should hold together with the validity. Like if we assume different corrupt players and different interpretations, why must their final
that's a
proposition
great
hold?
question. So I think you should, I'll let you think about it yourself. The thing to realize is that even though I'm viewing it in different ways, they're talking about the same experiment, which is the hexagon experiment. Like, you know, the same experiment, like there are different ways to look at it, but it doesn't change the nature of this experiment.
So it's like here, if we have M to be corrupt, and if M controls M, F, L prime, M prime, then L probably should be forced to be 1. But the thing is, we have F prime as a player instead of F. Is that allowed?
That is also okay, right? Because like essentially all of these are running the honest program. Like the honest program is well defined.
Okay.
Just saying, okay, you know, all these nodes are running the honest program. So by looking at the same experiment in 3 different ways, I mean, although there are 3 different ways to look at it, it's looking at the same experiment. I think that's the key thing to understand about the proof.
Okay.
And you know, if you ask why, I think you kind of, if you think about it yourself, you know, by construction, by definition of the experiment, you can realize that, like, even though there are 3 different interpretations, like it's talking about the same thing. It's just like there are 3 ways to think about it.
Elaine, I'm sorry, I think I still don't understand why considering like in one interpretation like F to be corrupt and in other interpretation L to be corrupt, why is it like only different interpretations? Like to me it sounds like it's different experiments.
So all of them is talking about the same experiment in which there are 6 players executing the honest program. But the only difference is in this interpretation, I will imagine that these honest programs these 4 honest programs are executed inside the mind of the same player.
Oh, I see. So we are actually like the experiment is actually like about 6 nodes and not like 3 nodes and.
Yeah.
Okay, I
Yeah,
see.
so
Okay.
it's always, the experiment is that there are 6 nodes speaking the honest program. But one way to view it is that these honest programs are being executed inside the mind of a single player. But because this player is executing the union of these 4 honest programs, it's actually not executing the honest program, right? Like if it is a single player, it's not executing the honest program of that single player, it's executing the union of 4 honest programs.
Okay.
Is it kind of like they, instead of have 1 corrupt player out of 3, they have basically 4 corrupt out of 6, kind of?
I mean, I guess like we are trying to rule out the existence of a protocol that defends against 1 corrupted player out of 3. So the way to rule it out is you have to look at the same execution and imagine somehow it's a 3-player execution where some of these things are just happening in the mind of the same player. So that's why we have to interpret it somehow, like it's a 6-player experiment and all 6 players are honest, but there are 3 ways to interpret it as a 3-player experiment where 1 player is executing a union of some honest nodes. But no matter which interpretation it is, it's still talking about the same experiment, right? If you think about the experiment, like no matter whether these players are executing in the minds of a single player or they're actually, like whether it's being virtualized or not, the effect is the same, right? The virtualization is like supposed to be identical, as if you didn't virtualize it, right? So this is just virtualizing all of this on a single machine, but it shouldn't change anything, the virtualization, right? Like,
but then how do you ensure at the end of the day that there was at most 1 corrupt party?
In each interpretation, there is at most 1, because like the way I mean, this is honest program, this is honest program. This is the virtualization of, it's a program that virtualizes 4 programs. But if I view it as a 3-player protocol, this virtualized program is not running the honest program, right? It's like running something else. It's like the union of these 4 things is not the honest program corresponding to a single player. Okay, so let me just, there are 4 minutes left and let me just finish the proof and I can stay longer if you have more questions. So in fact, actually, Junxi already finished the proof for me, right? So I just have to write it down. So let's recall what Junxi suggested. So we are going to view it as a 3-player execution involving M, L, and F prime. I mean, M is actually executing this. So let's say the 3-player execution is this big program virtualizing all of this. And then there's L and F prime. So in this 3-player execution, this is the corrupt node and these are honest. And by validity, we can conclude L must output the input of F prime, which is 1. So it's basically symmetric. Like I think if you kind of, like the key is just to get comfortable with the idea, all 3 interpretations, they're just different ways to view the same experiment. Okay, so interpretation 3 is that this is a 3-player experiment involving F prime, L, and M is corrupt and simulating M prime, F, and L prime.
So in interpretation 3, you're also assuming that F prime is the designated sender and its value is 1.
Yeah,
like
F prime is the, Yeah, it's the same experiment. So like in this experiment, we
assumed for the experiment F was the designated sender, right?
Well, there are two designated senders, F and F prime, and this receives input 0, this receives input 1. So since we are always talking about the same hexagon experiment, right? All these interpretations are different ways to view this experiment, right? So in the last interpretation, this is the designated sender, and it receives the input 1, and therefore by validity, L should output 1.
But in our system model, we just had one designated sender, right?
Yeah, by validity, let me write that L should output F primes input bit 1. So therefore we have reached the contradiction. Therefore, and the contradiction rules out the existence of a protocol pi that's among 3 players and that defends against one corrupted player. So we are actually on very good time. I can stay around longer if you have more questions about the proof. So this is actually like this proof is in some sense very simple, right? It just uses really elementary stuff. But I mean, when I actually learned about the proof, it took me several times. Like I felt like every time I read it, I understood it a little bit better. These lower bound proofs are also typically pretty subtle, right? So and also going back to the question, why doesn't the proof work when there are signatures? And that's because like when, let's say when you, you know, when we say F is simulating all of this in its head, like if there are signatures, like F wouldn't be able to simulate essentially L and M because it's not able to like produce their signatures. So that would fail. I mean, obviously the proof shouldn't work if there are signatures involved.
I'm wondering how do we interpret this experiment if all nodes are honest nodes? So if there's no corrupted node, then how should we interpret it? Or like by giving one of the F to have an input 0 and another F prime be input 1, we don't consider the situation about a no corrupted node anymore.
I mean, like if like when we define the experiment, like it involves 6 players, it's a hexagon and all of them are honest. But in order to reach the contradiction, we have to interpret in 3 different ways as a 3-player experiment. And only when we interpret it as a 3-player experiment can we apply the consistency and validity property of pi, right? I mean, we're trying to rule out pi, and the proof would not have been possible unless we use the consistency and validity property of pi, right? I mean, what makes pi impossible in some sense is like the consistency constraint and the validity constraint together, like they're in some sense conflicting each other. But now we want to defend against one corrupt player, right? Because there's one corrupt player among 3, having to satisfy both properties simultaneously imposes contradicting essentially constraints. So the proof has to make use of the properties of the protocol, which is consistency and validity. And if we just like look at it as a 6-player experiment where all players are honest, this is not supposed to be the way the protocol is executed because it's a 3-player protocol, but we can like, you know, have an experiment that's well defined with 6 honest players. Like there, we cannot reach any conclusion because it's not possible for us to apply the property of the protocol pi. And in order to apply the property of the protocol pi in the proof, we need to take the same execution, which is the hexagon execution, and interpret it in 3 different ways as a 3-player execution. But all of the interpretations are talking about the same experiment, and that's also important. Yeah, so that's why I guess that's also why I said in the beginning, like the magic of this proof is this hexagon experiment. Like, you know, you have to somehow get comfortable with the idea. There's this hexagon experiment, it's actually well defined. And then I can look at it in 3 different ways, as if it's like a 3-player experiment with each.
Is there proof for that, why this hexagon is well defined, or we just take it for granted?
You guys hear her?
Yeah, I cannot hear her.
Good,
Yeah,
yeah,
I-
I think.
I
Yeah.
can't hear.
Can anyone give her a call again? Maybe.
Let's try wave again.
I probably gotta go for now. I have a class like in 10 minutes.
Yeah, me too.
Oh yeah, I think you will.
Waving goodbye.
And now I'm on a
Goodbye.
different
Yeah.
device. So I guess I dropped. For how long have I been dropped?
A minute?
Like a minute or so.
Okay, well, that was not too bad. So I was just suggesting, yes, like it's helpful to think about the proof more offline. Like for me, it took me, like really, I read the proof like several times. I taught it several times, like over the course of a few years. And every time I read it, I felt like I understood something more. Like it's very easy to syntactically check that the proof is correct. But I feel like understanding it fully does take some time. And I think that's the beauty of this proof. Like it's so simple, and yet, like, you know, most lower bound proofs are kind of subtle. And I guess like one thing that always intrigues me is how they came up with the hexagon idea in the beginning, because that's like the magic of the proof. Okay. All right, yeah, if no more questions, it seems like, you know, the Zoom is like aware, like every time after an hour, it thinks the class should end, so it just cuts itself off.
Okay.
So to make sure I will never go over time. Okay, all right. So I'll see you on Thursday.
Yeah, Thursday. Thank you.
You.
And the homework is out, right? You have seen it on Canvas. It's due on Friday next week.
Yeah. Can you send the email to the student who are auditing the homework question?
I've emailed it to you. You can check your email.
Okay.
Oh, the homework. I guess I emailed the mini research project. The homework is pick 5 exercises in the textbook from the first 2 chapters, which is chapter 3 and 4. So exercises 1 to 7, pick any 5 and write an answer.
Okay, I see. Thank you.
All right. See you on Thursday. Bye.
Bye.
Thank you. Bye.